Good afternoon, respected teachers, estimated faculty members, fellow classmates, and distinguished participants. Thank you all for joining us today. My name is Nuaa Tamang, and on behalf of Group 2, it's my privilege to welcome you all to our innovative project presentation, the Sonic Aircraft Bird Deterrence System, SABDS. Bird strikes continue to represent one of the most persistent and costly safety hazards in modern aviation. In 2024 alone, the United States recorded more than 22,000 wildlife strikes on civil aircraft, a 14% increase year over year. While global economic losses are estimated to exceed $1.2 billion annually. These incidents not only threaten human lives and aircraft integrity, but also create operational disruption and environmental concerns. Our project addresses this long-standing challenge with a forward-looking, non-lethal technological solution, an aircraft-mounted AI-enabled acoustic deterrence system that detects birds in real time during the most critical phase of flight and safely redirects them using directional species-specific sonic pulses, all without harm to wildlife or interference with crew and passengers. Over the few minutes, we will guide you through the problem content of secondary data-driven market and stakeholder insights, the technical architecture, prototyping roadmap, acoustic and detection mechanism, operational safety features, and finally, the projected impact and path towards certification and commercialization. We have designed SABDS to be eco-friendly, certifiable, and economically compelling, a practical step towards safer skies for both people and birds. Thank you once again for being here. Let us proceed to our main presentation. Now, I want to show our introduction video.
Bird strikes are a billion-dollar threat to aviation safety, rising every year. In 2024 alone, over 22,000 cases were reported in the U.S., costing the industry $1.2 billion. The cost isn't just financial. It's about passenger safety and wildlife preservation. We need a smarter solution. Introducing SABDS, the Sonic Aircraft Bird Deterrence System, a revolutionary innovation designed to protect both the aircraft and the birds. SABS uses advanced radar and camera systems to continuously scan the flight path. Its onboard AI instantly analyzes threats, distinguishing birds from other objects in milliseconds. When a threat is confirmed, wing-mounted speakers emit a focused, directional sound beam. This creates a humane deterrent, guiding wildlife away from the danger zone without harm. Pilots stay informed with clear, non-intrusive alerts, keeping the cockpit environment calm and focused. Engineered for reliability, SABDS provides all-weather protection day or night. With autonomous solar-powered options, it's designed for efficiency and minimal maintenance. Projected to reduce bird strikes by up to 50%, drastically lowering repair costs. It's a humane, non-lethal approach that respects wildlife while ensuring passenger safety. Designed to integrate seamlessly, ensuring low pilot workload and DO 160 compliance. SABS is paving the way for safer skies and a more sustainable future for aviation. SABS, safer skies, protected wildlife.
A United plane was forced to return back to DIA last night after the airline says there was a wildlife strike after takeoff. Video shared by witnesses shows a plane with flames shooting out of the right engine. The plane landed safely back in Denver. No one was hurt. Everybody just got on another flight a few hours later. This latest incident raises more questions, though, about wildlife at our airport, and that's why we're going to bring in our 9 News aviation expert, Greg Feith. So when we talk about birds, we've heard about this before. If it was birds, what was that? Did they get sucked in, or what happens?
Typically, when you have a flock of birds and the aircraft encounters them, you got to remember those jet engines are sucking a lot of air. They're like giant vacuum cleaners. So if they fly through a flock of birds, they get ingested. You disrupt the smooth airflow of the air going through the engine. That's what causes what's called compressor stalls. That's what people saw as the airplane flew over. You saw the bursts of flames. That's the disrupted airflow, which causes an imbalance in fuel and everything else, and you will get that raw fuel being burned and exhausted out. That's what they saw.
But it's not something pilots aren't, they're trained to do something like
Pilots are trained to handle that kind of event. You can't avoid birds because birds will fly haphazardly. So pilots can't try and dodge the flock of birds, they fly through them. And the airplanes are certified and the engines are certified to take in at least an amount of birds and a particular size of birds. But if you remember the Miracle on the Hudson, when they took in 20-pound geese, now all of a sudden you have a real problem. The pilots, the airplane still stayed intact. It was just that it affected the performance of the engine.
Where you put an airport matters in that realm, as far as what kind of wildlife you have. If you have rural airports with deer and the like on the ground, that could affect a landing as much as anything. But birds are around airports everywhere.
Tom, as pilots, aviation, we share the sky with the birds. And so when you build an airport, you have to look at the migratory patterns. You have to look at all of the surrounding events. If you remember Old Stapleton, we had Bar Lake off the end of one runway. It's a bird sanctuary. We have eagles out there and a bunch of migratory birds. Here, unfortunately, I coined it Mount Trashmore, but we have a landfill right near the airport. Landfills always attract birds. So yes, you bring up a very good point, and that's what planners have to really look at. There are a lot of ways to mitigate birds. LaGuardia, perfect example with Miracle on the Hudson. They use cannons, they use dogs to try and chase the birds out. But we also had an unfortunate accident in South Korea with Jeju Airlines, where the airplane was on the approach, flew through a flock of birds. That caused a performance problem with the engines, and by the time the pilots were able to get the airplane back to the airport, unfortunately, they couldn't make a successful landing.
There's not much they can do, right? I mean, at this point,
speed, right?
We are as well defended as we can do against birds?
Right now we are. They're trying to come up with technology. They've been developing ultrasonic technology that would be emitted from the aircraft or even from the ground in the local area of an airport to try and scare the birds, but birds adjust to that. They use flashing lights. They use a variety of different things, but birds are birds. They're haphazard. They fly in a variety of different directions. We as pilots are always trained that if you encounter birds in the air, that the birds typically will dive, so you want to try and pull up, but you can't be yanking and banking the airplane all over the sky, especially a large transport airplane. Passengers won't like that e-ticket ride.
No.
Well, when the airport says wildlife strike, this could have conceivably been something else, and they were taking off and they hit that.
And that's what caught my attention, was the fact that they used the term wildlife instead of birds. Because wildlife, I've flown in and out of several airports here in Colorado where I've encountered coyotes on the runway, and a lot of other pilots have too. You can strike, an animal on the runway. There's a point that pilots, it's a go, no-go decision where you don't have enough runway to stop. So if you hit something, you keep flying. So if they did strike a coyote or some animal on the run, they have to fly and bring the airplane back around. So it's interesting that they use term wildlife and not a bird strike.
Well, hopefully there'll be more information forthcoming, but thanks for shedding some light on it for the rest of us who sit in 31E.
What was that?
You don't see what you get to see.
You just feel the effects in 31E.
Yes. Greg, it's good to see you. Thank you very much.
Hello, everyone. So first, let's discuss about our contents. First of all, we have the executive summary where we will be discussing about the introduction of innovative project service, and then our bird strike problem overview and key aviation case studies. And then objective is our vision and mission of the innovation market status. Then we have our business model, and then the key features of the innovative product and services like technical feasibilities, financial feasibilities, viability, and marketability. And then we have the product installation procedure and prototyping phases and installation procedures, technical mechanism of the device, overall system architecture and block diagram, detection mechanism, processing and decision mechanism. All of the thing will be discussed over there. Then we have the pre-launch survey analysis, and advantages and disadvantages of the project of our service, measure to overcome the disadvantages. We also discuss about this matter. Moving on, we have the life cycle of the project, how we will design it, and the overall design and architecture. Everything was discussed on that part. And project rationale, overall objectives, overall delivery of this project, how long it can take, and the methodologies we used to design this product and everything. Everything is introduced over there. And the project implementation, introduction, how we use to project to system components and interference overview, pre-flight procedures, in-flight operation, post-flight procedures, troubleshooting, and safety notes are everything mentioned over in this section. And then we have the problem and risk assessment plan, how we can do all these things and unfinished work, future improvements and everything. After that, we have the acknowledgements, and then we have our learning outcomes and our meeting minutes and every single thing we did in this course as a case studies. So we also discuss about this matter. So now let's begin with the executive summary. Good afternoon, everyone. I'm Zunayed, and I will be walking you through the executive summary, a key case study, and the vision and mission behind our innovative solution to one of our aviation's most persistent safety challenges, bird strikes. The problem. Bird strikes are not just a minor nuisance, they are a serious, costly, sometimes deadly threat to aviation safety. In US alone, there were over 22,000 reported bird strikes in 2024 and 2025. Globally, this incident causes more than 1.2 billion in damages every year. But beyond the numbers, there are real human stories, and one of the most famous is the miracle on the Hudson. Now we move to the case study, Miracle on Hudson. In 2009, US Airways Flight 1549 struck a flock Canada geese just after takeoff. Both engines failed. Captain Slangberg and his crew had to make an emergency landing on the Hudson River. All 155 people on board survived, but the incident exposed a critical gap in aviation safety. Engines were not designed to withstand large bird flocks. The event became a turning point in how we think about the bird strike prevention. Our solution, the SABDS, Sonic Aviation Bird Deterrence System, could have changed the outcome of the day. Using radar and AI, SABDS detects birds up to 500 meters ahead and emits non-lethal sonic pulse to redirect them away from the aircraft path. Moving on to the next slide, our vision and mission. So what we are trying to achieve, our vision, a world where bird strikes are virtually eliminated, safer skies for everyone. Our mission, to deploy a certified, humane, and affordable acoustic protection system for global aviation. We have set clear strategic objectives to guide us. Reduce bird strikes by 40 to 60% during takeoff and landing. Environment, 100% non-lethal, protecting both passengers and bird population. Economy, saves over 100,000 per avoided major strike with ROI within 2 years. Certification, achieve FAA and EASA approval, meeting all aviation safety standards. And marketing development, target high-risk regions first, aiming to equip 20% of the global commercial fleet within 5 years. And moving on to the next part, executive summary, recap to bring it all together. SABDS is an aircraft-mounted system that uses radar, AI, and directional sonic pulses to detect and deter birds in real time. Its effectiveness, detection up to 500 meters, deterrence within 200 meters, eco-friendly, non-lethal and low energy, technically sound, financially viable, and already supported by strong market research, with 85% awareness and 72% favorable feedback from aviation stakeholders. We believe SABDS represents a smart, scalable, and humane step forward in aviation safety, one that protects lives, assets, and wildlife. Thank you so much for your attention. I will now hand over to Kayum, who will dive into the market analysis and business models. Thank you.
Hello everyone, my name is Abdul Kaim Talukdar, and I'm excited to walk you through an innovative solution designed to make aviation safer for all of us. SABDS uses compact radar and cameras to detect birds in real time up to 500 meters away. It can even tell what types of bird it is using AI. Once a threat is confirmed, it sends out directional sonic pulses, like predator calls. to safely scare birds away without harming them. And it's lightweight, easy to install, and works automatically with the plane system. But there is more. Our system is eco-friendly, uses very little power, and is made from recyclable materials. It logs all bird encounters for later review, and pilots can take manual control if needed. Plus, the sound library can be customized for different regions. Overall, it's designed to keep flights safe without adding extra work for the crew. So, is this idea realistic? We did a full feasibility study looking at technical, financial, and market angles. We based everything on real bird strike data and cost. The goal was to make sure SABDS is practical, low risk, and fits within aviation safety rules, meeting today's needs and tomorrow's challenges. Technically, we are on solid ground. We are combining proven tech, bird radar, directional sound, and AI. With over 95% accuracy in threat detection, the system meets FAA standards, runs on low power, and has backup system in place. Similar acoustic systems are already used in wildlife control, so the concept is tested and ready. Here is a quick look at how it operates in flight. A radar detects a bird, alerts the pilot, and triggers the sonic emitters. The system sends out sound pulses that disappears the birds before they get too close. It's all processed by an onboard computer, giving the pilot a clear warning while keeping the sky safe. Of course, there are challenges. We designed the system to withstand vibration and weather, use shielding to prevent electrical interference, and build smart software to adjust for bad weather. We are also using 3D printing and off-the-shelf parts to speed up prototyping, wind tunnel, and sound chamber tests confirm it's durable and reliable. Now, let's talk cost. Development will talk about $2 million. Each unit cost $3,000 to make, and we will sell it for $50,000. Annual maintenance is low, around $500 per unit. We break even after selling 100 units per year, since a single bird strike can cost up to $1 million in repairs and delays. The savings add up fast. Financially, this is a smart investment. Bird strikes cost the industry over $1.2 billion a year. We can also earn from AI updates and data analytics. Even if costs rise, the model stays strong. Airlines could even see lower insurance premiums. For anyone focused on long-term safety, this is a win. The market is growing. Bird detection tech will reach nearly $240 million by 2035. Our system is so unique. It works in the air, during low altitude flight, and is non-lethal. With stricter safety rules and rising operational costs. Demand is strong, and because it's scalable and low maintenance, is sustainable for the long run. Here is our SWOT breakdown. Strengths. It's eco-friendly, proactive, and integrates smoothly. Weakness. Weather can affect performance and startup costs are high. Opportunities. More bird strikes mean more demand, plus new rules push adoptions. Threats. Competition from ground system and skepticism about effectiveness. Looking ahead, opportunities are clear: rising bird streaks, new regulations, and tech partnerships with AI and urban air mobility. Threats include existing competitors and doubts about performance. Our response: real world testing, adding hybrid features, and working closely with regulators to prove our value. That brings us to the end of my presentation. Thank you for your attention. Now, I would like to invite our next presenter, Junaid. who will walk you through the implementation roadmap.
Thank you, Kayum. Now we will move to the practical implementation of SABDS. The system features a modular low-impact installation strategy that integrates seamlessly with existing aircraft structures and avionics. Certified A&P technicians complete the installation in 4 to 8 hours per aircraft, ensuring minimal operational downtime. Prototyping follows an iterative, risk-reduced methodology aligned with FAA and EASA certification requirements, progressively validating technical concepts through structured testing. The overall architecture combines forward-facing sensor and an onboard Raspberry Pi-based AI processor, parametric acoustic transducers, and auxiliary photovoltaic power module to deliver autonomy, low electrical draw, and zero interference with primary flight systems. Moving on to the prototyping phase. Prototyping proceeds through 5 clearly defined phases. Phase 1 involves conceptual CAD modeling and aerodynamic simulation and optimized mounting layouts for aircraft compatibility. Phase 2 consists of component-level bench testing of radar, air processor, and acoustic emitters to verify detection accuracy, power consumption, and DO160 EMI compliance. Phase 3 conducts full environmental qualification, including vibration, thermal cycling from -40 degrees Celsius to +70 degrees Celsius, humidity exposure, and wind tunnel performance evaluation. Phase 4 encompasses field validation through ground vehicle trials, drone-mounted tests, and supervised flight evaluations to confirm operational realism. Each phase feeds directly into iterative refinement, systematically improving reliability, safety margins, and certification readiness. Next slide, we have technical system architecture. The architecture operates as a closed-loop, real-time AI-enabled bird deterrence system optimized for low-altitude flight phases. Sensor fusion merges millimeter wave radar with electro-optical and infrared cameras to achieve greater than 95% detection accuracy. The onboard AI processor analyzes bird trajectories, flock density, and collisions probability using adaptive thresholds conditioned on flight phase and environmental conditions. Upon threat confirmation, directional parametric transducers are activated. Power management is handled via solar PV module charger controllers and voltage regulators, minimizing craft electrical load while preserving fail-safe operation. Moving on to the detection and decision part. Detection and decision making are fully automated and tailored to high-risk phases. The system activates automatically before 10,000 feet, covering takeoff, climb, approach, and landing, where over 90% of bird strikes occur. Multi-sensor forward scanning with radar and electro-optical thermal cameras continuously monitors airspace to 500 meters in all-weather conditions. Onboard AI fuses sensor data to classify threats by size, velocity, and flock behavior. Collision risk assessed through trajectory, intersection probability, and projected paths. Acoustic deterrence is triggered only when the predefined risk threshold is exceeded. All detections, classification, and responses are logged for post-flight analysis and continuous system improvement. Moving on to acoustic emission and mounting. The acoustic subsystem relies on the parametric principles to deliver precise human deterrence. An ultrasonic carrier wave of 40 to 60 kHz is modulated with audible distress of predator calls 2 to 10 kHz, producing a highly directional forward beam approximately at 10 to 15 degree wide through nonlinear air propagation. Emissions rate peak intensities of 100 to 140 decibel in short, randomized 1 to 5 second pulses with an effective range about 200 meters, minimizing habituation. Transducer arrays are flash mounted on the wing landing edges inside aerodynamic IP67 rated fairing wing, less than 3 kg per array, ensuring negligible drag, full weather resistance, and structure compatibility. Next, we have the operational workflow and safety. Operational workflow is designed to be fully automatic and non-intrusive. Activation and continuous scanning occur automatically below 10,000 feet AI confirms threats and trigger directional emissions without requiring pilot intervention. Safety is assured through tightly focused beams inaudible to crew and passengers, automatic fail-safe deactivation on fault detection, manual cockpit override switch, complete DO-160 EMI shielding, passive alters only, and full environmental compliance, including non-lethal operation. IP67 weatherproofing and vibration and or shock resistance comprehensive event logging supports ongoing performance refinement. Together, these elements establish SABDS as a technically mature, certifiable solution capable of meaningfully reducing bird strike risk during critical flight phases. This technical foundation supports to projected performance gains and economic value. We now proceed to the implementation time and risk assessment. That's from me. Now I would love to welcome Farhan for the next part of the presentation.
Market status. Good afternoon, everyone. Let's begin with the current market status regarding bird strike in aviation. Bird strike incidents are a significant and persistent safety challenge in the aviation sector. Airlines face substantial costs due to aircraft damage and unscheduled maintenance, not to mention the operational and economic losses caused by flight delays. Current bird control measures show limited effectiveness and come with high operating costs with global air traffic on the rise. The risk of bird strike is intensifying. This creates a clear and urgent need for advanced automated bird deterrence solutions. As you can see from the FAA data reported to the wildlife strikes to US civil aircraft remained a consistent concern from 2010 through 2024. Now let's look at business model and the societal pain point. Our primary stakeholders are airports, airlines, and aviation regulatory bodies. We plan to commercialize this system as an integrated product complemented by installing services. Revenue will be generated through direct sales, maintenance, contract, and future system upgrades. For a societal perspective, bird strikes pose serious risks to passenger safety and aircraft reliability. These incidents lead to operational disruption and financial losses for both airlines and airports. By mitigating bird strikes, our solution contributes to not only to improve aviation safety but also supports environmental balance. Usefulness in real-world applications. Moving on to the real-world application, our system delivers tangible benefits. It enables early detection of bird activity in runway and airfield zones, helping to prevent catastrophic engine injection and structural damage to aircraft. This directly enhances overall flight safety and boosts airport operational efficiency. A key advantage is its ability to support continuous 24/7 monitoring with minimal human intervention. This solution is particularly applicable to airports located in high-risk ecological and geographic regions where bird activity is most challenging. Let's dive deeper into the pain point. Repeated bird strike incidents lead to high maintenance and repair costs. Flight delays and cancellation damage airline reputation and hurt passenger satisfaction. Current methods, often manual or traditional, lack consistency and reliability. They also face performance limitation in low visibility or adverse weather conditions. What the industry clearly needs is a dependable, automated solution that operates with low overhead and delivers consistent performance regardless of conditions. The visual here underscore one of the most visible consequences: delays, viability, and marketability. Finally, let's discuss why this solution is viable and marketable. The system feasibility is backed by established sensor and acoustic technologies. While there are initial implementation costs, the long-term benefits, reduced damage, fewer delays, lower maintenance, far outweigh these expenses. Our design is scalable, making it suitable for deployment across airports of all sizes. There is a strong market potential driven by strict international aviation safety standards. We anticipate high adoption prospects in both domestic and global aviation markets. This isn't just a product, this is a necessary evolution in aviation safety infrastructures.
Proceeding to the exhaustion equivalent is systematic compilation and validation of secondary datasets, publicly available FAA wildlife strikes report covering 1990-2024 with over 22,000 incidents recorded in 2024 alone. SEO Global summarized peer-reviewed literature on bird strike mitigation and aggregated professional commentary were collated using structured search and extraction protocol. Temperature trend, for example, annual strike increases, regional variation, and specific hazard were cross-verified across sources. Data quality control include removal of outdated or incomplete record across referencing of consistency and prioritization of high authority sources. FAA, ACAO, academic journals. This discipline synthesis yield a real-life consolidated evidence-based equivalent to a clean, high-quality dataset supporting robust analytical interference without primary sovereign. The adoption of this secondary data synthesis delivered several strategic advantages. It enabled precise alignment of SABTS feature with documentary and history priority, particularly around real-time detection. Eco-friendly deterrence and minimal integration burden, as reflected in existing reports. It facilitates early identification of adoption buried highlighted in prior analysis, allowing proactive design adjustments. The approach informed charged value proposition resonance with safety comments and regulator by focusing on high impact areas revolved in aggregated data and uncovering persistence gap, for example, limited in flight non-lethal options. Results efficiency was enhanced finally. It's demonstrated rigorous respect of established stakeholder evidence strengthening. The project's credibility and alignment with broad aviation safety discourse. Nevertheless, lenience on secondary data carries recognize limitations that must be acknowledged. Synthesis is results intensive in terms of sound identification, validation, and harmonization across disparate datasets. Selection and publication bias may exist with over representation of high-profile incidents or strongly opinionated experts' view. Finding may not fully capture emergent or underrepresented perspective and rapid evaluation in air traffic on wildlife patterns can render all the data reliance and aggregated qualitative commentary risk over generalizing or over-engineering around secondary priorities. To mitigate this limitation, deliberate countermeasures were applied throughout the process. Sources were rigorously selected for recency, authority, and methodological transparency, prioritizing FAA 2024-2025 reports and ACAO aligned data. Multiple and independent datasets were cross-validated to reduce single-source bias and improve representativeness. Temporal relevance was maintained by emphasizing the most current statistics. For example, 2024, strikes increases. A balanced analytical framework combined quantitative trend analysis, strike frequency, damage cost with technical review of excess committed, ensuring depth without over-interpretation. Finally, a specific language was minted between finding and SABDS design decision, preserving traceability and until intellectual rigor. This safeguard transforms inherent secondary data considered into controlled, acceptable level of uncertainty. This discipline secondary data methodological underpin the confidence in ACBDS market feed and technical direction. We know more through the core quantitative trend and prioritization application.
Thank you, Aya, for the insightful opening. While the technical challenge and history of bird strikes are well documented, solving a problem of this magnitude requires us to move beyond traditional reactive ground-based defenses. We are proposing a shift towards a proactive onboard solution that integrates directly into the aircraft's own ecosystem, ensuring protection is available wherever the pilot flies. To understand the necessity of the sonic aircraft bird deterrence system, we must look at why behind our innovation. Currently, bird strikes represent a critical and rapidly growing threat to global aviation safety. In the United States alone, we see over 22,000 annual incidents recorded. These are not merely minor inconveniences, they result in more than $1.2 billion in global damages every single year. Our research identified a significant market gap. Most existing solutions are ground-based, think airport radars or physical bird patrols. However, SABDS fills the critical onboard gap during takeoff and landing, which are the specific flight phases where 90% of all strikes occur. Our innovation is driven by three main pillars. Regulatory alignment. We are ensuring strict compliance with the FAA, ICAO, and EASA safety mandates. Environmental responsibility. We've committed to a human, non-lethal deterrence model that aligns with modern biodiversity conservation. Economic viability. We provide a clear return on investment for operators who face repair costs that can exceed $10 million for a single engine replacement. To address these drivers, we have established clear, measurable objectives that define our success. Our primary safety objective is ambitious. We aim to reduce bird strike incidents by 40% to 60% for equipped aircraft during high-risk, low-altitude phases. Ethically, we focus on species-specific technology, allowing us to manage wildlife humanly without resorting to lethal forces. Economically, we intend to deliver savings of over $100,000 per avoided major strike, ensuring the system pays for itself rapidly. Technically, we are targeting full FAA or EASA certification and ensuring compatibility across commercial, general, and even rotary wing aviation. Our long-term vision is to establish SABDS as a platform for future AI and multimodal enhancements, supporting the industry's ultimate zero-strike safety goals. Now, let's look at how this works. The architecture of SABDS is built on a core principle, the system that must be modular, aerodynamically efficient, and most importantly, lightweight. By keeping the total weight under 10 kg, we ensure it can be integrated into existing airframes without compromising performance. The system operates on a sophisticated closed-loop logic: detection, processing, decision, and then emission, and finally, feedback. Sensors. We use a fusion of forward-looking radar as the primary source and electro-optical camera as the secondary source to achieve over 95% detection accuracy at ranges up to around 500 meters. As for the processor, it's an AI-enabled processor such as NVIDIA Jetson, which handles real-time threat assessment. For emitters, we utilize directional parametric acoustic arrays to create a focused sound spotlight using bioacoustic pulses to safely steer birds away from the flight path. To maintain aircraft integrity, sensors are mounted in the nose radome, while emitters are placed on wing leading edges, all while remaining EMI shielded and DO-160 compliant. Finally, we have structured a 4-phase life cycle to ensure a sustainability from concept to decommissioning. Phase 1 involves 6 to 12 months of intensive R&D training, targeting a 10 to 15-year operational life for the hardware. Phase 2 focuses on scalable manufacturing and a certified installation process that requires minimal downtime, only 4 to 8 hours per aircraft. Phase 3 is our operational phase, utilizing over-the-air software updates to keep the AI threat library current against changing migration patterns. Phase 4 ensures component recycling in strict compliances with ROHS environmental regulations. We stand behind this with a 5-year limited warranty and a performance guarantee of at least 70% deterrence efficacy. But a sophisticated design is only as good as the plan used to bring it to life. To discuss our hybrid management methodology and our 18 to 24-month timeline, I will now pass the presentation to Nima. Thank you.
Thank you, Pretsha. Our project success hinges not just on brilliant idea, but on a disciplined and realistic plan to bring it to life. This brings us to project delivery. We have adopted a hybrid project management methodology. This strategically combines the waterfall model, which provides the essential structure, documentation, and phase gate we need for hardware development and rigorous certification process, with achievable Scrum sprint for the iterative, fast-paced development of our software and AI components. This hybrid model is the established best practice for the safety-critical aerospace innovation as it balances the need for regulatory traceability with the flexibility required for technological iteration. Our delivery is structured into a clear phase timeline of 18 to 24 months to achieve a market-ready prototype. Let me outline the key phases. Initiation and planning, month 1 to 3. Defining requirement, assembling the cross-functional team, and establishing the project baseline. Designing and prototyping, months 4 to 9. This is where CAD modeling, subsystem design, and component-level testing occurs, building the physical foundation of SAPTS. Integration and testing, month 10 to 15. The critical phase where we bring hardware and software together for ground tests, initial flight trials, and efficiency validation. Certification and pre-launch, month 16 to 20. A dedicated phase for preparing and submitting all documentation for regulatory approvals, targeting an FAA Supplemental Type Certificate or STC. Launch and deployment, month 21 or more. The transition to first customer installation and ongoing performance monitoring. Underpinning this entire timeline is a risk-managed education strategy. We maintain a live risk assessment matrix, ranking potential issues from R1 to R10 based on likelihood and impact. This allows for proactive mitigation strategies for high-priority items such as electromagnetic interference or certification delays, ensuring they do not derail our critical path. A clear methodology requires an effective team structure to execute it. Our project implementation was driven by a dedicated cross-functional team. Our project manager provided overarching oversight of the timeline, budget, and stakeholder coordination. Technical leads were appointed to direct specialized work streams in hardware engineering, software development, and system integration. The core engineering team comprised aerospace engineering, AI software developer, and biotic specialists, ensuring depth of expertise in every critical domain. This structure ensured focus, deep work within each discipline while maintaining tight integration toward our shared project goal. Education followed a systematic phase sequence. We begin by establishing the supply chain for critical components and initializing parallel development tracks for hardware and software. Major subsystems like the radar processor and acoustic emitter arrays were integrated at predefined engineering milestones. Testing followed a rigorous iterative protocol starting with laboratory bench tests, progressing to environmental stress testing in chambers, and culminating in final flight validation. Continuous documentation was made at every step, creating the auditable trail necessary for future certification with aviation authorities. The process concluded with comprehensive system verification and validation, proving that the system was built right and it was the right system to solve the bird strike problem. Any aviation system must be designed with the pilot in mind. The SAPDS interface is engineered for seamless cockpit integration. System status, alerts, and manual controls are accessed directly through the aircraft's existing multifunction display. The pre-flight procedure is minimal, requiring only a quick status verification via our built-in test. Crucially, the system activates automatically based on the aircraft's flight phase and altitude, aligning with pilots' expectations and standard operational flows. This design philosophy minimizes pilot workload while ensuring system readiness, adhering strictly to standard aviation human factors principle for safety and usability. In operation, the system functions autonomously. During flight, it continuously scans, detects, and if necessary, activates deterrence without pilot input. The pilot is notified of our activation via a standard non-intrusive cockpit alert. Pilot response is typically limited to alert acknowledgement with a manual override switch available if ever needed. Post-flight, all event logs are automatically available for review by maintenance and safety teams, supporting continuous improvements and incident analysis. It is vital to state that SAPDS is classified as an adversary safety enhancement. It does not replace established pilot procedures like visual scanning or communication with air traffic control. It is a layer of automated proactive protection added to the existing safety ecosystem. To ground this in our academic content, we developed a detailed 18-month activity plan for our university-led proof of concept. This plan is realistically scoped, accounting for academic schedules and research constraints. It is divided into 5 sequential phases: planning, designing, prototyping, testing, and closure. Each phase has clear deliveries and review gates to ensure disciplined progress. Please note that this timeline brings us to a functional prototype. It does not include the additional extensive duration required for full regulatory certification, which would be the focus of subsequent commercial phase. This DANTT chart provides a visual representation of that 18-month schedule, showing parallel work streams and key dependencies. Major milestones such as design reviews and test readiness reviews are clearly marked as critical decision points. Alongside scheduling, we'll proactively identify key envisaged problems. Technical risks include electromagnetic interference and ensuring consistent system efficacy across diverse environments. Regulatory and market adoption risks also present significant challenges. To address risks, we have developed a formal risk assessment plan. Our risk assessment management follows a structural approach. We conduct a formal assessment using a likelihood impact matrix to prioritize risks. High priority risks such as certification delays and electromagnetic compatibility issues have been assigned dedicated mitigation strategies. For technical risks, mitigation involves early compliance testing and designing in hardware redundancy. For regulatory risks, the strategy is proactive, early engagement with authorities to align our deployment with their requirements. This is not a static document. Continuous monitoring of this risks register is a standard part of our project management practice. While we have developed a robust proof of concept, transitioning to a certified product requires significant further work. Our primary recommendation for the next phase are: first, comprehensive flight testing and long-term field studies are essential to gather irrefutable performance data across seasons and geographies. Second, achieving full regulatory certification is a critical resource-intensive milestone that must be the central focus of commercial partners. Third, product development must focus on cost optimization and manufacturing scalability to achieve our target price point. Finally, future work should explore hybrid multimodal deterrence, perhaps combining acoustics with visual ones to increase efficacy. This outlines a clear and necessary pathway for subsequent deployment. Beyond the immediate product, this product establishes a platform for substantial future research. Key opportunities lie in predictive AI using migratory pattern data, adaptation for urban air mobility vehicles like air taxi, and building global bioacoustic libraries for species-specific deterrence. Regarding safety, safe operation is not negotiable. It requires adherence to defined pre-flight and in-flight procedure. Pilot and maintenance crew must be adequately trained on system operation and limitation. Any system fault must be managed by a clear protocol. Deactivation and reversion to standard procedure. Safety is paramount and has been integrated into every aspect of the system design and operational protocol. This journey has been much about the processes as the product. I'll share the key lessons I'm taking forward as a team leader. First, interdisciplinary innovation demands intentional communication. We had to consequently build bridges between engineer, programmer, and domain expert and creating a shared language. Second, regulatory requirement must be foundational, not an afterthought. We learn to design for certification from day one. Third, real-world validation is indispensable. What works in simulation must be proven in the field. Fourth, successful innovation requires balancing ambitious vision with practical constraint. We navigate the constant tension between ideal performance and feasible executions. Fifth, a sustainability focus provides significant strategic and ethical value. Strengths are proposal immeasurability. And finally, academic project management benefit greatly from modular milestone-driven planning. It keeps a complex project on track and manageable.
By doing this project, I evolved from simply contributing ideas to becoming a dedicated facilitator of structured inquiry. I learned to elevate the quality of our collective thinking by consistently applying Socratic questioning, root cause analysis, and intellectual standards of clarity, precision, and relevance. They sharpened our decision making and helped us move beyond incremental ideas towards genuine innovation.
Finally, this project was more than just a product pitch. It was a powerful learning experience for our team. We want to extend our sincere thanks to our professor, Mr. Wallace, and our team leader, deputy team leader, and all of the members, especially Mr. Wallace for his invaluable guidance, mentorship, and for teaching us the skills needed to bring this project to life. Under his direction, we sharpened our problem solving and analytical thinking, improved our teamwork and presentation abilities, and learned to apply creative solutions to real world challenges. Thank you, Mr. Wallace, and thank you all.
Every year, bird strike causes over 1.2 billion in damages to aircraft worldwide. They delay flights, damage engines, and most importantly, risk passenger safety. Current solutions are often inconsistent, disruptive, or reactive. This is why our team Group 2 developed the concept for the sonic aircraft bird deterrence system, or the SAPTS. It's a proactive onboard system designed to prevent bird strike before they happen. You may ask how SAPTS work. The core idea is simple. Equip aircraft with sonic emitters that produce non-lethal aversive sound frequencies and specifically tuned to birds. These emitters actively during high-risk phases, taxi, takeoff, and landing, creating an invisible sonic shield that safely encourages birds to move away from the aircraft's path. The sounds are designed to be effective for birds but harmless and barely noticeable to humans and aircraft structure. Beyond the concept itself, developing SABDS provided us with key learning outcomes. First, system thinking in aviation safety. We learned to view the airport as an interconnected ecosystem. Our solution had to consider wildlife biology, airport operation, and aircraft engineering and safety regulation as one unified challenge. Second, innovative application of bioacoustics. We moved from theory to practical research, studying how birds perceive round sound. We investigated which frequencies and pulse patterns effectively deter without causing harm or leading to habitation. Third, balancing innovation with practicality. A great idea must be feasible. We engaged with real-world constraints like system-wide power use, aviation certification standards, and pilot interface. This taught us to design for implementation and not just for innovation. Fourth, the engineering design process. We applied the full circle from problem identification to research to concept design and schematic development and planning for simulation and testing. This structured approach turned an idea into a detailed proposal. Fifth, collaborative technical communication. We learned to communicate a complex technical idea to different audiences, from engineers to airport managers. Crafting clear presentation, reports, and justification was as crucial as the design itself. Conclusion, the SAPS represents a shift philosophy from reaction to a bird strike to preventing them intelligently. Through this project, we didn't just design a system, we practiced the essential skills of modern engineering, a holistic analysis, applied science, practical design, and clear communication. Thank you. This is presented by Group 2.
Through my role in presenting the project rationale, overall objectives, and technical architecture of SABDS, I cultivated a deeper and more structured approach to problem solving and solution design within a complex, real-world context. This experience significantly enhanced my ability to deconstruct a multifaceted challenge, such as bird strikes in aviation, into its core components: safety, necessity, market gap analysis, regulatory alignment, environmental responsibility, and economic viability. I learned to construct a persuasive, evidence-based narrative that not only justifies the need for innovation, but also logically connects each design decision to a strategic objective. In explaining the system's architecture, I developed the skill to translate highly technical concepts such as sensor fusion, AI-enabled processing, and parametric acoustics into clear, accessible language without sacrificing accuracy or detail. This process reinforced the importance of audience awareness in technical communication, ensuring that both experts and general listeners could grasp the value and functionality of our proposal. Furthermore, I refined my ability to set clear, measurable, and realistic project goals, balancing ambition with feasibility by framing our objectives around specific metrics, such as a 40 to 60% reduction in bird strikes and a defined return on investment. I practiced aligning project vision with tangible outcomes. This segment of the presentation also taught me the importance of life cycle thinking in engineering design, considering not only the implementation and operation of a system, but also its long-term sustainability from manufacturing and updates through end-of-life recycling. Overall, this responsibility strengthened my competency in integrative thinking, persuasive presentation, and project framing, skills essential for leading innovative projects and communicating their value in professional and academic settings. Thank you.
I've learned that true innovation isn't accidental, it's built by design. It's balancing today's success with tomorrow's possibility and valuing both exploration and exhaustion. Creativity, trip, and discomfort, hearing people who challenge us, encouraging debates, and protecting early ideas. Traditional management often stifle this by prioritizing harmony over breakthrough thinking. Leadership and innovation demand humility. We must listen more than we speak, watch the fridge for weeks final, and consciously spend our time building the future, not just management the present. Ultimately, innovation is a team effort. It needs diverse thinker, a tolerance for failure, and the courage to act, not just analysis. Thank you.
Music like this is an education in itself, extending far beyond the technical syllabus. As a team leader, my core learning was not just in system engineering, but in systems thinking applied to human collaboration. I evolved from a participant to a dedicated facilitator of structured inquiry, focusing less on my own ideas and more on evaluating the quality of the team's collective thinking. I learned to guide decisions using stochastic questioning to challenge unexamined assumption and root cause analysis to ensure we were solving fundamental problems, not just symptoms. I recognized that the quality of our output depended entirely on the intellectual standards we upheld. Therefore, I consequently modeled and insisted on clarity, precision, and relevance in all our communication, which sharpened our focus and elevated our entire decision-making process. Finally, my key role became synthesis, integrating the team's diverse perspective using system thinking to map how individual insights interconnected and analogical reasoning to adapt creative framework from unrelated fields.
Bird strikes remains a serious and escalating threat. More than 22,000 incidents were reported in the United States in 2024 alone, with the global damages exceeding $1.2 billion annually. Existing ground-based mitigation strategies leave a critical protection gap during the takeoff, climb, and approach. The landing phase is precisely where the vast majority of strikes occur. As the BDS bridges this gap through an integrated aircraft-mounted solution that combines real-time multi-sensor detection, AI-driven threat assessment, and directional human acoustic deterrence, all without compromising crew safety, passengers' comfort, or aircraft performance. Our analysis, grounded in FAA and ICAO data, secondary stakeholder insights, and rigorous technical evaluation, confirms its strong feasibility. The system leverages proven off-the-shelf components, achieves high detection accuracy, integrates safely with existing avionics, and targets up to 50% reduction in strike incidents on equipped aircraft. Beyond safety and cost savings, SABDS aligns with global priorities with sustainable, non-lethal wildlife management and demonstrates clean economic viability in the market, increasingly pressured by rising air traffic and habitat incoherent with continued refinement and certification supports. SABDS has realistic potential to evolve from an innovative concept to standard inherence for safer, more sustainable in the aviation. Before we close, we should like to express our deepest gratitude first and foremost to Professor Wallace. Thank you for providing us with this challenging yet inspiring opportunity and for your continuous encouragement throughout the semester. We are indebted to the foundational data and authoritative research published by FAA, ICAO, and the global wildlife hazards research community, without which this project would lack its essential evidence base. Our sincere appreciation goes to the faculty advisors at Nuaa for their expert guidance, critical feedback, and unwavering support. We also thank our fellow classmates and our team members for the tireless collaboration, creative input, and shared commitment to excellence. This project exists because of the collective expertise, generosity, and belief of everyone who contributed directly or indirectly. Thank you all from the bottom of our hearts. Now we will showcase our reports and our learning throughout the whole course. First, report pages.
These case stories, I have learned that creativity and innovations are not instant gifts, but the result of deliberate habits, structured practice, and disciplined routine. True innovations requires embracing counterintuitive strategies like hiring for discomfort, rewarding productive failures, and protecting early ideas from premature judgment. I now understand that critical thinking is not just about questioning information, but about actively seeking contradictions, inflections, and extreme uses to reveal future opportunities. It also requires balancing exploration with exploitation and managing multiple time horizons simultaneously, optimizing the present while selectively abandoning the past to build the future. More importantly, I have learned that innovation is a collective responsibility, not confined to certain roles at the department. It thrives where there is constructive conflict, diversity of thought, and leaders who commit wholeheartedly, creating environments whose convictions and actions turn novel ideas into reality. This course has taught me the most powerful strategies are those that are stress tested, flexible enough for multiple futures, and embedded in daily practices, turning critical thought into meaningful, innovative action.
From Khan Academy case, this case reinforced the idea of taking agency over your own learning, moving away from passive education toward self-paced. Mastery is not just for students, it's a lifelong skill, especially in business, where curiosity often beats the curriculum. From SBR, where rules of creativity case, I learned that hiring people from diverse and irrelevant backgrounds sparks greater collective imagination. Innovation needs safe havens away from the core business, and sometimes selling an idea with conviction is more important than calculating its odds. From creativity case, creativity is not a gift. It's built through habit, and hard work. This case taught me to embrace misfits, reward action over inaction, and accept failure as essential to innovation. True creativity blends structure with chaos. From weird ideas that sparks innovation case, true innovation often feels like rebellion, not improvement. Organizational harmony can hide complacency. To innovate, you sometimes have to break the rules you once succeeded with and learn to tolerate discomfort. From the three-box case, balancing present performance with future innovation means different rules for different boxes. You can't ask your core business to innovate. It needs separate process, funded by today's profits, but protected from short-term pressure. From focus of successful futurist case, now I can see that futurists are not just R&D. They look for rare signals of coming change. Productive tension between creators and logicians is healthy. And if you cannot measure your impact on a trend, you are just watching, not shaping it. From planned opportunism using weak signals to spur innovation case, the best leaders don't just react, they shape the future through planned opportunism. This means staying sensitive to weak signals and having structured response ready so the wrong future doesn't overwhelm the right one. From putting the innovator's DNA into practice case, finally, leadership in innovation is about shielding ideas, not just steering them. Passionate belief often trumps cautious analysis, and leaders must personally model curiosity, experimentation, and the willingness to question everything.
Hi everyone, I'm Ilbadawi Ayan. This semester has been a deep dive into the heart of innovation, unlearning old myths, embracing discomfort, and redefining what it means to build creative future within Minsight. What started as a study of business and design thinking turned into a personal journey of understanding how creativity thrives in shows and how leadership, teamwork, and foresight shape meaningful innovation. I began the semester with a narrow view of creativity. I thought it was an innate talent reserved for idea people and artists, but studying Twila Trapp and Robert I. Sutton Phillips that one its head. Trapp taught me creativity is a habit built through routine and hard work, not just natural gifts. With Sutton research revealed that traditional management practices obsessed with efficiency and harmony are actively hostile to creativity. I realized that the most valuable creative contributors aren't the easy team members. They're the slow learning who challenge the status quo, the heretic who make you unforgettable, and this taught me to stop fearing conflicts and start seeing it as sharpening tool for ideas. A core lesson was the critical tension between exploitation, refining proven methods, and exploration, chasing improved ideas. Companies and individuals fail when they lean too hard on one side. I learned to practice flattening and focusing, brainstorming willingly, then narrowing down with analytical rigor, while also grappling with the duality dilemma. The conflict between visionary and pragmatist in large organization that isn't a flaw but a trait. A successful team harness this duality to bring right brand creativity and lift brain logical into innovation leadership, redefining itself for me this semester too. I used to think leadership was about authority and having all the answer, but now I know it's about humility. The three-box solution framework struck me later. must audit their attention, as where you spend your time reveals your true priority, not your strategic plan. And also, I learned that the arrogance of past success is the biggest killer of future potential, pushing me to practice, listen to learn. Uh, Thinking ideas from outsider, ignoring rank, and and uh, shielding creative team from unnecessary pressure to perform from bosses of customers. Foresight isn't about predicting the future, it's about seeing it early, and I learned to observe the fringe, recognizing that the real change happening not the mainstream, but with the hackers, academic and experimental thinker on the margin. Weak signal detection become a skill I practice systemizing how I spot early trend intake demographics and customer behavior using tools like Ultimatrix and mix insider-outsider groups. Also, understanding the patient is a futurist's most vital skill, as isolated signal mean nothing, and you have to wait for persons to emerge before action. I used to think a team of idea people was the gold standard. Now I know it's a recipe for failure. This semester I learned that complementary discovery skill make team trip. The idea generator need exhauster, that surface level diversity plan in comparison to diversity of thinking styles. Um, the T-shaped individual dip in one idea, broad in other are the glue. Innovative teams and the innovation flows need different skills mixed at every stage. Um, well, well, also seeing how financial rigidity kills breakthrough ideas. By prioritizing short-term profits over the higher failure rate essential for big wins. Beyond the technical skills, this semester rooting me in personal value that guide my approach to innovation. Education must be personal to standardized. As true innovation happen when learned, adaptation to individual curiosity. Technology should serve curiosity, not replace human teaching. Leadership is empathy and vision, not authority and work-life. Balance isn't a luxury. It's a requirement for creativity. I also embrace that learning is a lifelong. Feedback is process, not criticism, and patient projects start as simple ideas, drive by purpose. Um, this semester wasn't just about learning outcomes on paper. It was about building a mindset. I live with toolkits to foster creativity, lead with humility, spot future trends, and turn reality into straight. Most importantly, I know that innovation isn't about being perfect. It's about being brave enough to act, to fail, and to keep exploring. Thank you for your joining my journey.
Through this project, I have developed a critical understanding of innovation as a disciplined process rather than a sporadic act of genius. I learned that sustainable creativity requires balancing the refinement of current systems with the deliberate exploration of untested ideas. Key insights include the strategic value of cognitive diversity and constructive friction within teams, the necessity of protecting dissent and learning from intelligent failure, and the importance of institutionalizing foresight by systematically scanning for weak signals. Furthermore, I recognize that true leadership and innovation involves intellectual humility, a willingness to selectively abandon past successes, and the ability to allocate strategic attention across managing the present, abandoning the obsolete, and creating the future. Thank you.
Good day, everyone. Based on the 6 case study presentation from Group 2, These are the consolidated learning outcome for each one. First case study is about HBR, the weird rules of creativity, which I think the learning outcome for this topic is that students will understand the traditional measurement practices focused on efficiency after hiding creativity. They will learn to apply counter-intuitive strategies such as hiring misfits, rewarding failure, fostering defiance, and balancing exploration with exploitation to cultivate innovation environments. For the second topic, for the second case study, is the weird ideas that spark innovation. For that, I think the outcome will be that students will recognize the innovation requires practices that may feel uncomfortable or unconventional. They will be able to identify and apply techniques that challenge norms, encourage diverse thinking, and embrace failure as necessary step forwards toward breakthrough ideas. The third topic is forgetting the past and managing the present, the strategy of the great innovators. For this topic, I think the learning outcome is that students will learn to apply the three-box framework to manage organizational strategy across the three time horizons, managing the present, selectively abandoning the past, and creating the future. They will understand how to avoid a success trap and allocate resources for sustainable innovation. For the fourth one, focus on successful futurists. The learning outcome about this topic, I think, will be that student will develop skill and strategic foresight by learning to detect weak signals and use frameworks like Sci-Fire and Flare and Focus and plan for multiple future scenarios. They will understand how to balance creative and logical thinking to shape, not just predict the future. For the fifth case study, it's about planned opportunities, using weak signals to spur innovation. For this, I think the learning outcome is the student will learn to systematically identify weak signals of change and translate them into actionable hypotheses. They will understand how to design and run low-cost experiments, learn from the outcomes, and build an adaptive, resilient organizational culture. Sixth is the innovator's DNA. And this is one of my favorite. For this, I think the learning outcome will be that student will identify and develop the 5 key skills of innovative leaders: question, observing, networking, experimenting, and associate thinking. They will learn to build complementary teams, balance discovery with delivery, and foster a culture where innovation is everyone's responsibility. For the last one is called Life is Work, Reflection on Samar Khan and Khan Academy. The learning outcome is that students will reflect on the role of curiosity, self-directed learning, and purpose-driven leadership in education and work. They will understand how technology and empathy and iterative feedback can transform learning and inspire lifelong critical thinking. Thank you for your time.
I would like to share the most powerful lessons we took away from the Harvard Business Review case studies and innovation articles we explored during the course. We begin with one that deeply resonates with all of us. Salman Khan's insight that life is work. Through studying his journey with Khan Academy, we realized that true innovation rarely comes from isolated genius moments. It emerges from sustained, curious, self-directed lifelong learning. We learn that the most impactful contributors are not necessarily the most talented at the start, but those who remain creative, curious, and capable of conceiving and implementing novel ideas over many years. This reminded us that education, innovation, and personal growth are lifelong habits, not events, and that real success lies in how much we help others grow along the way. Next, Robert Sutton's HBR article on the weird rules of creativity challenges many of our assumptions. We discovered that high-performing, innovative organizations often took strange or even dysfunctional by conventional standards. Sutton taught us that creativity isn't about wild talent as much as it is about productivity. You have to generate a huge volume of ideas, most of which we all fail because breakthrough success is fundamentally a numbers of game. We also internalized his famous test organization character, what happened when people make mistakes. The best culture treat intelligent failure as fuel for learning, not as punishment. The shift is mindset, embracing weirdness, tolerating dissent, and protecting nascent ideas from premature judgment. Fundamentally challenge how we now view team dynamics and risk taking. Drawing from multiple HBR cases, including Vijay Govinder's work on planned opportunism and managing three time box 1%, box 2 abandon the past, and box 3 create the future. Jeff Dyer, Hal Gergerson, Clayton Christensen, Innovators DNA, Thorpe's Creativity Step by Step, and others are groups distilled several shared understanding. Passion often beats pure analysis in the early stages of innovation. Yet, discipline and retention turn passion into real breakthroughs. Too much expertise can blind teams. Beginners and outsiders frequently see what insiders means. Innovation belongs to everyone, not just R&D. The real enemy is inside. Rigid rules, fear of failure, and comfort with the status quo. Successful organizations practice planned opportunism. They listen to weak signals for the fringes, translate them into low-cost experiments, learn fast from both success and failures, and selectively abandon the past to create space for the future. Creativity is a habit cultivated through routine, curiosity, discomfort, diversity, and failure-tolerant culture, not a rare gift. Leaders must personally model innovation, protect constraints, and reward action and learning, and balance exploration with exploitation across all three timeframes. This principle, drawn directly from the Harvard cases, now guide we have approach problems, evaluate ideas, build teams, and think about our own future contributions. In short, this course didn't just teach us about innovation theory, it changed how we think, collaborate, take risks, and view failure. We are living more reflective, more courageous, and far better prepared to contribute meaningfully in uncertain. Thank you for letting me share these collective insights. Next, we have the meeting minutes. Ladies and gentlemen, respected professors and dear classmates, as we conclude today, let me leave you with a simple truth. The skies are safer when we refuse to accept preventable risk and when we dare to innovate with both courage and compassion, as a BDS is more than a technical concept. It is our shared belief that aviation can protect lives, reduce costs, and respect wildlife all at once. We have shown at a thoughtful blend of radar, AI, directional acoustics, and rigorous prototyping can meaningfully reduce bird strike incidents during the most vulnerable phases of flight. We are deeply gratitude for your attention, your questions, and opportunity to present this work. Thank you to Professor Wallace and for your guidance and everything, to our teammates for countless hours of collaboration, and to every one of you for being the part of this journey. Thank you so much.